Hello, I'm Sheikh Amanullah. I'm a grad student from Professor Abhishek Dey's group. Throughout my PhD tenure, I have been trying to understand why nature had to synthesize a variety of heme enzymes having different heme architectures. For this presentation, I'll be trying to understand why cytochrome C containing nitrite reductases reduces nitrite to ammonia, while cytochrome Cd1 nitrite reductase, they reduce nitrite to NO. Now, if you take a closer look to their basic distal superstructure, it's almost like similar, and both of them contains end-donor axial ligand. The major difference is their heme active site. In the case of CcNiR, this is heme C, while in the case of Cd1NiR, this is heme D1. And if you compare them, you will find in the case of heme D1, there is 2 electron-withdrawing keto group as well as 2 saturated carbon centers. And if you look at the proposed mechanistic cycle, you will find that it's almost like similar. First reduction, binding with nitrite, protonation to release water, forming FeNO6. Then in the case of Cd1NiR, there occurs an electron transfer, and in the case of CcNiR, there occurs a proton-coupled electron transfer, forming FeNO7. This is the last common intermediate between these two enzymes. In the case of Cd1NiR, nitrite comes and releases NO. In the case of CcNiR, there occurs another PCT to form FeHNO8, which further protonation and electron transfer releases ammonia. Now the question is, why CcNiR does not undergo NO release and Cd1NiR does not undergo PCT process? And we found a correlation between NO stretching frequency and rate of NO release. We find that the higher the NO stretching frequency, greater is the rate of NO release, and this is completely macrocycle dependent. That's why we decided to go with the model complexes to differentiate the reactivity between heme C and heme D1. We chose iron TPP, which is having no electron withdrawing group, no saturated carbon centers, iron TPC having 2 saturated carbon, iron diester porphyrin having 2 electron withdrawing group, iron tetraester porphyrin having 4 electron withdrawing group, and iron diester chlorine, which is having 2 electron withdrawing group as well as 2 saturated carbon centers. Since FeNO7 is the last common intermediate, we made their corresponding FeNO7 adducts, and from the stretching figures, we find that if you have electron withdrawing group as well as saturation, all from weaker adducts. And from DFT calculations, we find that if you have electron withdrawing group or saturation, that actually lowers down the energy of macrocycle pi star, and there occurs and it becomes relative to pi star, and there occurs competitive back bonding, and that's why they form weaker adduct. Now, this is the particular reaction actually operating in the case of Cd1NiR, that nitrite comes and releases NO. We find this NO dissociation is highest in the case of iron diester chloride. Now, let us consider this particular step, which is actually operating in the case of CcNiR. We can actually get the information. We found that BDFE is lowest in the case of iron diester chloride. So now we can answer the question. In the case of heme C, it contains strong iron N bond, and that's why it prevents from NO release, while this is not the case with heme D1. It forms very weak FeNO bond. And in the case of heme C, this bond dissociation free energy is pretty high. That's why it undergoes facile PCT, while in the case of heme D1, BDFE is low. That's why it cannot undergo this PCT process. And this is probably the reason that CcNiR and Cd1NiR, they react differently. So thank you very much for your attention. I'll be happy to answer any question.